YouTube is just weird. I'm trying to make it restart. Okay, it shows me live, but it looks like everything is in a different place. I'm not sure even the link is the same. Oh my goodness, guys. I sure hope this is working. So, are you seeing, you're seeing something, okay. Are you guys here? It's a new link. I'm so sorry. I have no idea why YouTube did not like what was set up. My goodness. Now, hang on a sec. Let me pop out the chat so I can at least see you. I will not be able to put the, well, yeah, I can. I'll be able to put the chat there. Hold on a second. Oh, wow. Okay, you guys will not be able to see your own chat today. I apologize for that because this is my backup way of doing things. So give me a moment while I put this up here. And I will just put this here. Okay. All right, so hopefully you guys are being able to rejoin me now that I've got a bad link everywhere. Oh, it is what it is. Hi guys. You know, YouTube does what YouTube does, and when they change stuff around, who knows what is going to happen. All right, where's my cute little thing? So yes, we have a very interesting set of storms coming today. You guys able to hear me and see me? Yes, red shirt. Yes, yes. Are you able to hear me and see me? I hope. Yeah? Okay, cool. Awesome. Yeah, I said I had a workaround. I always do, right? Because I'm so used to YouTube being like this that I have to have a workaround. Otherwise, you know, you just never know when something's going to break. Okay, cool. Great, guys. Thanks for hanging in there while this gets all, you know, worked out. So I have two computers up today because I'm going to switch back and forth because we have some fun visualizations that we'll go through. But I will first give you the BLUF. Thanks for sticking around. And talk about, you know, the details of these storms. These are the first time I'm going through the charts, so, you know, I just put together the forecast, and this will be my first time running through it. So let's hope I can do it pretty well, okay? And yes, I will get to a lot of your questions as time goes on. So let's get into it. This is the forecast briefing. It's a solar storm forecast for the 11th. You will see 5-day outlooks having the 10th and, or having the tomorrow on through the 5-day. So it'll be good for tomorrow through what, the 16th or something, 17th maybe. Okay, so as you can probably see right there, boom, we've already had, this is one of our big flares. I kind of started off with this one back on the 7th. And you know, you may not realize it, but as we go into the deep dive, I will show you we are in the legs of a big solar storm right now. Anybody who's familiar with looking at solar wind data will know. They'll look at it and go, ooh, this looks like we're in a solar storm. Yes, we are, but we are actually in the legs, and I'll talk about why that is in the 5-day, I mean in the deep dive. But it may be one of these structures that was launched, you know, way away from Earth, or so we thought. And instead, what's happening is because these structures are a lot wider and angled, pretty close to you know, what we call low inclination, that they are being kind of funneled in a way that allows them to hit Earth when we don't think they would. So that's what's been going on this last day, and I do believe that it's maybe slowing down the storms that are still coming, and we'll talk more about that as we get into the visualizer. So here's one of the big flares from the 7th. I'm only going to focus mainly on the ones that launched the solar storms that we know are Earth directed. You'll see one here just very shortly. The big players here are region 4274 mainly, and 4272. These are the regions, actually, are these reversed? These are the regions here, and it's this big filament that we'll talk about here in just a second that has been just constantly shedding bits and pieces of itself. And we will also talk about the coronal holes. So keep your eyes on these coronal holes over here because they play a very big role in all of this in terms of channeling these puppies to us. So back on about the 9th, you'll see we're getting really, really active here. We definitely, and I took off the numbers here so that you could actually see the beauty of this. We have just a ton of involvement, not only this very long filament structure here, but also a ton of involvement from multiple places. And you'll watch it lift off. Look at this. You can even see the, how often do you see the fire? That's literally a fiery flux rope right there, because the fire itself looks like it's helical. Isn't that amazing? So there we go. You can see that when that launched the first Earth-directed solar storm, that's the one we're waiting for right now. I don't think it's going to hit us quite the way people might believe. A lot of people are thinking that this is going to be the strongest of the crew. I'm not necessarily sure that's true, and we'll talk about why. Even though it is completely Earth-directed, I think it has a much higher tilt than some of the others, but we'll talk about that in the deep dive. So here we go with that one. Just shortly thereafter, we have a second one. You'll see it fire on the 10th. Hold on, wait for it, wait for it. Where is it? Boom, right there. Doesn't look as exciting, but this is the one that's more Earth-directed. This is why it's dead center in the Earth strike zone, and this one is a bit tilted a little bit lower because it actually involved a bit more down here, and we'll talk more about that in a sec. So that's the second one. This is also a faster structure, so it's going to plow into the back of the first. We will get into that with both the NOAA and the NASA model runs. But that's the second one, and then you can see here in coronagraphs, here is the first structure coming out. Very, very asymmetric halo, very, very high inclination. If you can kind of follow this, you imagine the line of symmetry in here, and you can see kind of a vague structure that's the shock wave that's coming all the way around. But the main bulk of this structure is over in here, so up basically north and west of us, but definitely crossing the central meridian, because that's what we look for, right? We look for the crossing of that central meridian to see whether or not, and the equator, to see essentially whether or not we're going to get hit by that structure. It's a rule of thumb, right? Things get deflected in the solar wind, but you know, coming out of the sun, it's a good, if you see it, that it's going to cross through that central meridian and cross the equator, basically the cross you can see right there in the middle here. That's a very good sign that we do have something that could be Earth-directed, I mean really Earth-directed, and give us a really good storm. So that was the first one. Here's the second one on the 10th. You can see a lot more symmetric. This one's moving a little bit faster, but once again, the bulk of the structure is moving more to the west. A lot more stuff going on down below the central meridian. There's no doubt, because this is a full halo now, no doubt that we're going to get some of this structure. This is part of the shock wave on this side. It's also coming around here, but you can't really tell because it's just so much junk in the way. But you might notice a little bit of a curlicue kind of thing like that. Yeah, there's something going like this, believe it or not, kind of nestled like a little baby, and we'll talk about why that is later on. Okay, so that's the second one. And now, believe it or not, that's not the only one. So we'll be doing this twice, right? So those are the first two, and let's talk a little bit about them. I'm pulling up the potential field source surface model with 304 angstroms. Keep in mind, this is a coronal hole in here, okay? Keep in mind, this is a coronal hole in here, okay? I'm saying that on purpose because I want you to kind of notice that this whole set of regions, 4274 and 4272, they're both kind of, you know, like corralled in by these coronal holes on either side. And that's super important, especially when we start looking at this one, okay? And we'll talk more about that as we get to the next eruption. But those coronal holes they're fast wind streams, kind of create guide rails. It's kind of like, you know, if you're going bowling, right, and you put up the gutter rails so that your ball doesn't hit the gutter and go off. Yeah, you roll the ball and boom, boom, boom. That's what these kind of serve as. So they kind of keep that big coronal mass ejection that's coming out kind of locked in. So this is a very interesting situation that we've got here, because I think it's, in our case, it's actually helping us if you're an Aurora photographer. Of course, if you're anyone else that absolutely hates these solar storms, you're going, oh, what is happening? But yeah, okay, so keep that in mind. Also, and it's hard to see here, but you'll see it in a minute when I switch to a different wavelength. Notice the closed loops here in this potential field source surface model. This is as I talked about last week in my forecast, this is the coronal streamer belt coming up like this, and then takes a really sharp turn and then comes back down this way. Well, notice when these loops come back down this way, right? It's like a big long tunnel. The loops come back down this way. Look what they're overlying. Yeah, that's that filament. This is the filament that keeps erupting time and time and time again. So it's this really sharp bend that makes this very unstable, comes in like this, and then of course we have flux growth underneath this structure. So my goodness, it's just lighting off like a Christmas tree. So that when this whole structure goes, okay, it's not just this short area up in here. A lot of this stuff in here goes. Okay, and we'll see that especially on the eruption, that the third of the three. Okay, so anyway, wanted to keep that in mind just so that you can see that. We're going to flip back, because you'll see there's the second big eruption there, and you can see that coronal hole a little bit better. But we're going to flip back. There's the, actually, no, my fault. It's the 9th. That was an earlier one. Okay, so let me, since that shows so well, I thought I started this earlier, but since that shows so well, you can see how many different eruptions were occurring during this period. So it doesn't surprise me at all, because there's like back-to-back storms that are going off to the east of us. Doesn't surprise me at all that we're in the legs of one of these structures right now. And yes, those structures can kind of slow us down a little bit with some of these new ones, because they can't cannibalize each other. Okay, they have to actually wait. So there was the first one. Here's the second one coming up. Where is it? It's kind of hard to see on the 10th. There it is, whoosh, kind of not super exciting, but I do think that one's a better hit for Earth, but we'll talk about that in a minute. And now we're going to switch here to our 284 angstroms, which is a little bit higher in the corona. You can see those field lines a bit better now, can't you? Yeah, that's one thing. So here's the filament channel that we were talking about, okay? And see how it curves all the way around? But it's really guiding this kind of structure. So you're seeing something that's going to be kind of nestled like this. If I'm the sun, kind of nestling that little thing like a baby. And as it comes out, it's going to be tilted on this side and kind of flat on this side, because that's exactly the direction that this set of coronal loops are going. Okay, those are the overlying loops. Now, before we move away from 284 angstroms for a moment, notice you've got that coronal hole right here, and it might even be a little bit in here. It's kind of hard to tell with some of this overlying field. It's kind of hard to tell if the coronal hole branches this way or branches this way underneath all this. Because these are active regions, they're going to slice right through that coronal hole. They don't care, because they've got their own rules that they've got to follow. But that's the situation here. So you've got this coronal hole that's actually quite extensive, and the coronal hole on this side that just kind of keeps all this stuff in its own lane. Okay, so in just a second you can see a little bit more as it unfolds. All right, so now let's talk about the last event, right? The one that happened earlier today. We're still sitting right here. You can't see that coronal hole anymore, but you can see this one. You can even see it in 211 angstroms. You can see the pink, the dark coming way down. And when we have this big last event, as I fires here just a second, come on, fire, boom, right there. Okay, not only was this, what, an X 5.1, so pretty substantial event, right? And as you'd expect, always seems to happen, some of the biggest events start happening in the latter part of the declining phase. So we're beginning to enter that phase now, which is why we're seeing some of this. A lot of people believe that we should be continuing to ramp up activity until, well, at least until December, and then things might calm back down, because this is another Rossby surge that we're having here. But notice this coronal hole, and watch even down in here. You'll watch it as I back up just a smidge. Watch this edge and watch this edge. Boom. Do you see how I'm opening them up? See that? Can you see where all these dimming regions are? So that tells you that this particular event, okay, even though it was way over here, had involvement all the way down in here. And again, if you take that line, right, and you cross from the equator, and you cross the central meridian, you go, that's Earth. If you have, essentially, if you have some type of material or some type of involvement on the sun that hits this central area, good chance that there's going to be parts of it that are Earth directed. So you be the judge, right? Look for these little lines, watch them disappear. Poof. See that? I believe that this particular event is still going to hit us. Okay. And when we take a look at this in coronagraphs, once again, beautiful halo. Come on, back up. Sadly, if I can back up a little, there we go. Beautiful halo. Sadly, it's a really ratty, because we have an insane radiation storm that was launched with this. And what I mean by insane is, yeah, okay, fine. It's only, what, an S2 right now, right? But if you looked at the 100 MeV particles, the super high energy particles, how about the 500 MeV particles? This may be the strongest radiation storm we've had in terms of energy in maybe I think definitely in this entire solar cycle. Maybe even stronger than anything we saw in solar cycle 24. This is a very strong radiation storm. Fluxes aren't that super high, but the energies are high. We call this a hard spectrum, okay? So these are the ones that are going to affect aviators. If you're flying right now, if you're a high-risk passenger, if you're a crew, please take this into consideration in your flight plans. If you have implantable medical devices, please, be aware that you may have single event effects in these devices if you are required to fly, especially at high altitudes and high latitudes right now. If you can at all put off your travel for the next few days, might be worth your while if you are a high-risk passenger. But that is between you, your doctor, and God. That's all I can say. At any rate, is it dangerous for normal flyers? No, not at all. I mean, you're going to get a few extra X-rays, maybe a chest X-ray, but you'll be fine. I just worry about the high-risk passengers or those who are carrying newborn, prenatals. That's this is just high radiation period right now, so it's something that you should really talk with your doctor about. Okay, so yes, the high radiation is affecting the coronagraphs. That's why they look so ratty right now. It's what we call a blizzard. And so what you see, even though you can't really tell, this is a very strong shock wave. Okay, the fact that we can see it through the blizzard tells you something. Plus a lot of material, both above and below the central meridian. And again, it looks like at least the bottom edge of the bulk of the material, which is on this side here, because this is part of that shock wave. The bulk of that material is down. It did cross through central meridian, just as we saw crossing through central meridian on the source region. So I do believe that this is, even though the main of it, the thing that lit up was over here, I do believe there was enough overlying field in this that got launched, because we did see dimming regions clear down into this region. I have not had a chance to take a look at the coronal wave, but I guarantee you that coronal wave claimed at least clear down to here. Okay, probably stopped at the edge of this coronal hole, because coronal holes create kind of like boundaries. Kind of like, think of them as like big lakes, where stuff, cars can't, they dive into the lake and they disappear. So you can think of it that way. Don't think of it the physics that way, but that's, anyway. Okay, so yes, one more, right? So one more that is likely going to hit Earth, and is it going to give us as big a hit? Hard to say, but it will give us something. Okay, this is the only one I have not modeled with the visualizer. Sadly, I haven't had a chance yet. Okay, now let this go. Now, let's take a look once again at this with 284 angstroms. This is a little bit higher up in the corona, so now you'll see the involvement a lot better. So watch this region in here and watch it propagate clear down into this area. Do you see that? So let me back it up just a smidge. Boom. Can you see this? Watch this. It's involvement clear up and in here. Boom. Did you see it even lit up? If I back it up just a smidge, look at this. Come on. Look at that. Activation all the way up in here. So there are definitely some material clear down into this region that has been liberated and is on its way to Earth. Will it be a beautiful flux rope structure? I don't know if we're going to see that part. That you can see, for those who know what flare ribbons look like, you can see them here. There's the two flare ribbon, and then, or two ribbon flare rather, and then you can see that's where that big filament once again lit off part of itself and is launched out. So the neat thing is that Solar Orbiter will probably get a front row seat for this one. Solar Orbiter is already seeing some other data as well, because it's a bit higher than Earth. It's off the ecliptic plane a little bit. But see this coronal hole and see it kind of down here. We've got a more elongation and more widening of the boundaries of the coronal hole. So I think we may see this coronal hole enlarge as time goes on. Now, to kind of talk about it once again, here's the X1.8 class flare that we had back on the 9th. Here's the X1.2 on the 10th. Notice it's a little bit longer. I do believe this was a very energetic structure, even though it doesn't look like it's going to be giving us as much. I do believe that this structure is the one that comes from this X1.2 is actually going to give us a better hit than we think. And then the X5.1. And are we done? Yeah, I don't think so, because as we take a look at region 4270, is it 4272 or 4274? I have to look. I forget. That might read a 4. Sorry about that. The two were pushed together, but it's one region now, and you can actually see. There's still a lot of areas where we have what are called delta spots. It's very, very unstable. The area that's actively working, so if you can see the red in here, you don't want red and blue touching each other. The white is just showing where the actual sunspots are, so you can see the umbra and the penumbra. The penumbra is the lighter shadow. You don't want red and blue to be in the same penumbra, okay? If they are touching each other, that's not good. And so that's where things start lighting up. In fact, so you see where some of these regions are connected, or where you get the wrong color spot in the wrong place, those things are not, they're conducive for X-class flares. In fact, this latest X5.1, actually, boom, right here, it ended up happening in this region right here. So we have some emerging flux. You can even see it kind of clearing out right there. It almost turns green for a moment. That tells you a lot of flux cleared out. So we have some active incursion incursions right here, maybe some active flux emergence. We need to keep our eyes still on this region. I don't think things are going away quite yet. It may continue to be active over this, until it rotates off the disk. Likely we'll see something, what? I don't know, every 24 hours? Let's see. That's kind of a rule of thumb you use when you look at X-ray flux, when you see these big events. Let's see, almost midday on the 9th, almost midday on the 10th, almost midday on the 11th. Right, so these big flares, so what do you think? Maybe almost midday on the 12th? Gee, am I like some wizard? No, it's just the way it works. It takes that long to load the gun and fire again. So expect more fireworks from this set of regions, as time goes on. Okay, now, all right. Hopefully that was a nice little run through. Now we're going to talk about the model. And no, I don't have Noah's newest model. Whoops, let me back up a little. Noah's newest model has a little boop right here. It's kind of silly. It has this teeny tiny little boop right there, which is the result for the third event. But I was putting this together too early. So this is Noah's version of Enlil. It's our solar storm prediction model. You're looking down at the sun from the North Pole with Earth being off to the right. When I set it in motion, you will see one. That's the slow one with the X18. This is not an X18 storm. It was just associated with an X18 flare. Do not conflate solar storms with solar flares or you will be disappointed. You will see big X-class flares and think something great is coming toward Earth. And maybe nothing's coming. Because big flares and big storms don't always concert, okay? So here was an X1.8 that was associated with this particular storm. This one was associated with the X12, and then we don't see the X51, if I recall. Yeah, we don't have that one in here, but Noah's newest storm has it, and it's moving off very, very rapidly towards stereo A. All right, so as you can see, as we get really close to, the end of the 11th, these two storms kind of merge. They get close, right? This merging, which Nat Gopalswamy coined CME cannibalism so many years ago, thinking it was a cute thing, and then the media ran with it, thinking that it was like a small fish getting eaten by a bigger fish, and a bigger fish eats that, and it's not how it works. The model here is not a magnetic model. There's magnetic field in here, but it's just along for the ride. It doesn't exert any forces. Magnetic models that exert forces will not let these two things completely combine into a single mush pot. Okay, they are magnets, so they don't necessarily like to be next to each other, especially ones that are likely oriented the same way. So they're not necessarily going to merge very easily. Their edges might, right? You might get a shock that propagates into the backside of one. You might see a little bit of reconnection at the very end, so they connect just a little bit, but they're not going to smush into a single structure like you see here. This is just because this model has to run faster than real time, so we can't account for all of those details. So that's why they smush together. But expect to get hit somewhere late on the 22nd, on the 11th. The solar orbiter data is showing that it's pretty much in time with what we're going to see here. But then we will get another hit, right? The bulk of the second storm should be hitting us a little bit later, so expect continuous storming or expect a composite event by sometime on the 12th. So for those of you who like to look at solar wind data, expect to see a bit of a mess, right, by the time early morning comes on the 12th. I do think that'll be when it peaks. I do believe the peak of the storm will be on the 12th. And then we'll see a little bit of waning, and then the third storm will come, and that will give us yet another pop, but I don't think it's going to be as strong. So I do think the second one is where we're going to see the bulk of stuff, but it's not going to be because these two storms merge. I think it's because the second storm is oriented a bit lower, a bit more, not so highly inclined. Okay, and as a matter of fact, let's get into that. Let's see if I can get this to fast forward to the visualizer. Oh wait, first let's talk about NASA. Okay, so that was the NOAA prediction model. Here's NASA's prediction, and this one I did end up catching all three storms. So here's NASA. They did one that had two of them together, thank goodness. So you can see by the 18th they were saying we were going to almost get there. I think the actual impact time was about the 20th. So that's, the 2000 UTC. So we're about there right now. And yes, we are getting very close. We'll talk about it in the deep dive. and then we get that second hit. Here they're not showing that second hit being all that intense, meaning that it's a bit off axis. I honestly believe it's going to be a better hit than the first one. So we shall see. But again, early by the 20th, or early on the 12th, we should be seeing the second impact. Okay, and then here's the third one, and you'll see it launches really fast. In fact, I think I slow this thing down. It launches very, very quickly, and we're going to get, at least NASA is showing that there's going to get a decent edge-on impact. I think there's a very good chance that we'll see exactly that. But I don't think we're going to see the solar storm slinky unless this thing is really, really big for that third event. I think we'll probably get more of just the overlying envelope. So expect storming to last easily through the 13th, possibly late and through the 13th. Into the 14th before things begin to calm down. And then, of course, believe it or not, we will have a little bit of a fast wind chaser after that. Won't be all that much, but it might be something. So it'll be very interesting this week for things like Aurora. And yes, expect that the amateur radio bands in both GPS, and radio bands in particular are going to be a mess over the next, 3 or 4 days, because these solar storms, right, as they take the radiation storm with it, the radiation storm stays strong until these storms pass. Once they hit us and their shock hits, in fact, the radiation storms will likely get worse. They'll probably peak on the 12th and then again on the 13th before they begin to calm down. And that is simply because we have to get through the shock wave of these storms that are in front, that are being driven by the solar storm. Okay, so let's take now another look. You recognize this, but now this is the Enlil spiral for NOAA's version of the model. And hopefully you're seeing those two storms. And now I've overlaid the visualizer, and I did these quickly, so it's not a perfect overlay, right? But it gives you an idea that, yes, these two storms, as they come out, according to NASA's version of the model, the speeds are such that you will see these two interacting by the time they reach Earth. Are they going to just run over each other? No. And does my visualizer handle that? No, not yet. So we'll have to do them one at a time, okay? So let's talk about the very first one, and we'll get into that now. As we take a look at this, I'm just doing this as a movie here at the moment. After in the deep dive, I will actually go in with a live version, and I can give you guys the link so that you can actually play with the live version of these models. They're up on Patreon right now, by the way, so you can actually see them. And play with the actual animations. It's not just a movie. And it's much better to see than having to see a movie. So what I did here is that, let me back it up a little bit because I didn't talk about it. So I took that view that Enlil had, right, that from the side, right? So here's Earth. If I pull it back a little bit more, you see where Earth was, right? So this looks very similar to what Enlil looked like. And so here's Earth. We're looking down at the sun from the North Pole. Here's Earth. And now we're going to pull up into the ecliptic plane and rotate Earth so that it's along the Earth-Sun line. So it's like you're looking exactly at what Earth saw, okay? And I will, in the deep dive, talk about the coronagraphs and show you why I made the models, the tilt, and did the orientations the way I did. But this is that first storm that's going to be hitting us on the 9th. Notice this storm is highly inclined, and I got that information from both SOHO LASCO's imagery as well as Stereo A's imagery. So I'm not just willy-nilly putting these orientations on these big flux ropes like this, okay? This gold limniscate, okay, this is basically the boundary. This is what NASA and NOAA used to model the actual input, the actual solar storms themselves when they see them on coronagraphs. I simply put a flux rope structure inside it and then tweaked it empirically to look like, so that it fit the coronagraph images, the fine detail in the coronagraph images as best I could. Okay, so we will talk more about that in the deep dive. But so this is why I say the first storm, we may not hit the actual solar or the solar slinky core. We may actually just go through this darker blue stuff, which is just the envelope. Okay, so there may not be some pretty rotation of the structure at all. Will we hit the legs of this structure? I don't think so. That's if this thing is not completely distorted, which I don't think it will be, because it's a strong structure and it's being kind of corralled. Remember I said it's being kind of nestled like a baby because you've got the coronal hole on one side and on the other. So I think these structures are going to come out pretty close to the way that they launched off the sun, which will be something like that. So here's the second one, and now we're doing the same thing. We're rotating Earth, if I can get it there eventually. hopefully, okay, well, I got it, yeah. So there's Earth aligned with the sun, looking straight down the barrel, you know, along the Earth-Sun line. Here is the gold lemniscate, right, that NASA used to do their model. Notice I have this thing tilted a little bit differently. It's a lot lower inclination tilt. The leg also sticks out on this side. That actually matches the shock wave front. I actually did that on both, and you'll see that in the deep dive. This is how I kind of help decide what angle this structure should be at, is because of the way the shock looks and because of just the symmetry of the structures, the fine detail. So this one looks like it's going to be a lower inclination structure, so as it goes over us, there is a much better chance that we will actually see the solar slinky core of this. And because this one is a low inclination structure, this means that this should have some southward field and some northward field in it. Whereas the other one, which was highly inclined, that one either will give us strong southward field, like a ton of it, or it will give us only northward field, and we're not going to see much of the southward field at all. Okay, so it'll be either strongly north or strongly south. This one will give us a little bit of both, and that's just simply from the orientation of these structures that we see. Okay, so hopefully that's going to be the case. But again, I'll answer a lot more questions about that and the visualizer, and show the visualizers for these two ropes in the deep dive. Okay, so now switching to our moon, we are now passing through what the third quarter phase on our way to a new moon. With the new moon, well, the new moon's not going to be hitting us for another, like the 18th or something, but by the 16th, the moon will still be about 12% illuminated. You can see, so sadly, we are going to have some competition with the moon. So be sure to check your local rise and set times. But, you know, it shouldn't be too bad. At least it's not a full moon now. Okay, so now I'm going to move on to our 5-day forecast here. For our solar storm, high latitude aurora, solar storm conditions and aurora possibilities, I am deviating a little bit from SWPC. Maybe they've caught up now. It's almost, yeah, they may have, I don't know if they put up their new forecast yet. But I am going to say at high latitudes to expect a severe storm, probably a G3. Okay. In fact, I'm saying about an 85% chance of a severe storm starting around the 12th. Expect that to continue through the 13th. I did decide to calm down a little bit on the 13th. But we could still see very strong and a strong impact from that second solar storm. Things could die down to a G2 and then a G1. Then, of course, as we get to the 14th and 15th, we're really going to start calming down. But we could start looking for that wind watch, maybe even late on the 15th into the 16th. Not going to be very, very strong. Not expecting all that much from this fast wind, but it is something to consider. So those of you who are aurora chasers, I would say your chances of getting some aurora this week are very, very good. Prioritize clear skies over location, to be honest, because there's a good chance if we're going to get some aurora from all this stuff, you'll probably be pretty much anywhere you want at mid latitudes. Okay, I was going to say something else, I can't remember what it was, but yeah. The biggest impact is going to be likely on the 12th, both early and then for the first storm, and then late between the 12th and the 13th for the second storm. That's going to smash into the first. And then we're going to get into this latest one that's going to also impact sometime in there as well. So most of the storming is going to be between the 12th and the 13th. Okay, don't wait for the 14th to see if you can see something, because things may have calmed down by then. All right, so that's right, I didn't need to do that. All right, at mid-latitudes, well, we are also expecting a severe storm. Again, I'm probably deviating from NASA a little bit. I am expecting that we will reach G3 levels. I don't know if we'll reach G4. It's kind of tough to say. Again, the orientation of the magnetic field has to be the right way, especially in that first storm. But I'm giving us a chance of about 70% chance for a severe storm at mid-latitudes. Again, things will calm down after the 13th. Going to calm down a lot faster. The 14th, we may not see all that much, and then we'll have to wait until maybe the 16th or so to see some fast solar wind. So again, get your licks in early on the 12th and the 13th, because things could die down reasonably quickly. All right. And now switching to our solar flare and Dayside radio blackout outlook over the coming week, we are at a severe noise level. We expected this. This was coming. We saw it all on the far side of the sun last week. So we knew this was coming. And I've just kind of stretched out the 75% chance of M-class flares at the R1 to R2 level radio blackout for the foreseeable 5-day, because this region is still going to be firing stuff even on the west limb. We might calm down just a little bit. We have about a 35% chance of X-class flares. Might calm down a little bit by the 16th because it'll be rotating behind the west limb, but then that chance for radiation storms is going to open up a bit. So if you are a frequent flyer, and this does include air crew, right, watch those ICAO advisories, because those radio blackouts, especially at high latitudes, for those flying into the sun or away from the sun, that could be a real problem for you guys right now, because there's just a ton of noise, and there's that radiation storm that you have to deal with at high latitudes as well. Okay, and now switching to our radiation storm and polar aviation outlook over the coming week. We are well into the D2 minor range right now. This is a very stormy period. We are sitting at S2 levels. Likely tomorrow we will also be sitting at tomorrow and the next day sitting at S2 levels. And that's because we have to go through those shock waves of those solar storms. Once they hit us, those shock waves will actually cause, whoops, what happened? Once we get those shock waves, once they hit us, let me do this again. Play, please. Oh, I was playing and I didn't see it on the screen. How interesting. Okay. I'll just pause it for a second. Those solar storms, once they reach Earth, as they pass over Earth, they're going to cause those radiation storm fluxes to really peak. So even if we don't stay, I'm not necessarily saying that we're going to stay at S2 levels for the entire time over the next couple days. We may dip below them, but then we'll pop back up again as we pass through yet another shock. We have 3 interplanetary shocks out there that we have to deal with. So those will keep us storming easily through the 13th. Then we probably will dip down below the S1 level starting around the 14th, but probably pop back up, you know, and kind of ride the turbulent downward spiral as those solar storms begin to move further and further away from us. By the time we get to the 15th or so, we should be back to elevated, and hopefully down to the 16th, things will be back to, I'm hoping D1 normal range, but we may still see some of the noise and you know, just straggly radiation coming from it. So just expect that over the next few days. Okay, so Aurora photographers, as a nice summary, Aurora photographers, you should get some decent showing from literally, like, you know, moments away from now. We do have a preconditioned Earth right now, so if we're going to start storming, we'll probably storm pretty hot and heavy. As a matter of fact, I'll look at that in the deep dive to see how preconditioned we are. And so Earth may pop up to strong storm levels right away and give you some really great substorms as it begins to light off. So if you're an Aurora photographer, even down at mid-latitudes, good shows are in store. If you know someone who knows how to chase substorms, catch on, you know, hold on to them, because they can really let you know when things are going to brighten up and calm down. But either way, you should be able to get some really great shows, even with cell phone cameras. And now amateur radio operators and emergency responders, right now high latitudes are a disaster, okay? Expect that the radiation storms are just going to continue to pummel us over the next couple days, especially the high energy stuff. That's a real problem right now. So expect navigation, GPS, GNSS. If you're high latitudes, that is going to be an issue for you. Also, the Dayside radio bands are getting hammered, right? Every 24 hours, we're getting at least a radio blackout that's going to last for maybe an hour or two before things calm down. So just kind of hunker down. Then, of course, on the night side, things are bad. Well, will be bad here shortly. So if everything goes to hell in a handbasket, just, you know, kind of bear with it. I haven't looked, and I hope there aren't any hurricanes out there right now, or any major disasters that people need to deal with, because first responding is going to be a bit tough for you. So stay safe, folks. Okay, and then obviously for you GPS users and you pilots, if you are flying UAVs, right, calibrate the magnetometer often. You're going to get drift. You're going to get lots of things that'll throw you off. Also, dawn and dusk will probably be a total nightmare, as will high latitudes and anywhere near Aurora once those solar storms happen. So be aware of that. Also, you pilots, even in commercial flights, if you're flying into the sun, you know, near sunrise or sunset, or in a perpetual sunrise or sunset, especially at high latitudes, please, you know, be aware that those radiation storms, along with the radio blackouts, can cause some real havoc for you. So understand that VHF communications is going to be noisy, very noisy, for quite some time. Okay, so take that in consideration and pay attention to those ICAO advisories. And that, folks, I think is it for the main forecast. I know this was a long one, but thanks for sticking with me. And now I can answer some questions, and then we can go into some of the more fun stuff. Okay. Anybody have questions? Can I show the solar wind? Yes, I will. I'll show from Solar Orbiter. Yes, I think I have that up as a matter of fact, so yes. How about atmospheric drag? Yeah, that'll be bad. I don't think it's going to be nearly like what we had with the Gannon storm, right? That was 8 solar storms back to back to back to back. I don't think we're going to get anything close to that. But is a G4 level out of the question? No, not at all. And then, you know, we already are suffering a little bit with just some perpetual, you know, solar storming because of the fast solar winds. So atmospheric inflation sure is a problem right now. And we shall see. Hopefully Elon is, you know, being smart with his Starlinks and pulling them, you know, trying to thrust them a little bit higher than normal, because if they're sitting around 350 kilometers, those are the ones that are going to be coming down. So is Starlink rain in our forecast? Hard to say right now, but if he's got a lot of low-lying satellites, yeah, you might see a bit more re-entering than normal. Okay, so watch those splash zones. I hope they all stay over the ocean. But yeah, that might be a, you could definitely expect the probability for a little Starlink rain to be up higher than normal. Okay, what about Uber? Yeah, the driverless cars. I'm not as, you know, and Uber and you know, trying to get GPS. It could be for single frequency GPS. It could be an issue. It depends upon, again, it depends upon your latitude, depends upon what time of day it is, right? It's always catch as catch can. So just stay vigilant and retry. If something isn't working and you get, you know, it gives you a weird place, try again, and then wait another few minutes and try again. You know, sometimes it's sometimes that might be a little bit better. If you're nowhere near Aurora, well, then just travel at night. If you don't worry about Aurora too much, GPS will be fine if you do, especially if you do it at night, right? You don't have to worry about any of that stuff. Daytime with these big radio blackouts could be an issue, or if you're at high latitudes, that could be a real problem. GPS is known, GNSS is known to already have issues at higher latitudes, and now that we have this big radiation storm over the next couple days, yeah, I could see that being a little troublesome. So if you are using GPS to chase Aurora, please do not let that be your only method, and do not trust GPS blindly. There have been multiple occurrences of Aurora photographers who have run out into the field chasing Aurora, looking for wonderful things, and getting off of the road, not seeing it because it's snowy and the roads are covered with snow, and so they get lost and they get stuck because they were using their GPS thinking their GPS is working properly, and it's not. So you know, the reception is off. The satellites are just fine. It's the reception that is off. So be very careful and do not blindly follow your GPS if you're doing that type of stuff, especially in environments that you don't know, where you've never been, okay? That's just especially for those who are chasing Aurora for the first time, or are not very, you know, are not familiar with the area that you're chasing Aurora in. If the weather is inclement, you know, and you can't see the roads very well, just be very careful, okay? So hopefully that answers that question. Okay. How are the satellites protected against flares? Solar flares don't really do anything to satellites. They drown out satellite signals because it's basically when the sun screams. When you have a solar flare, the sun is screaming in radio noise, right? And it can scream a lot louder than a satellite can chirp. I always talk about it like the cricket in the train tracks, right? The cricket is next to the train tracks chirping happily. And you can hear the cricket fine as long as there isn't a train going by. But as soon as that train goes by, it drowns out the cricket, and you have no idea what's happened to the cricket until the train disappears, and then you hear the cricket chirping just happily. Nothing happened to the cricket. It's just it got drowned out. And that's what happens with big solar flares. Now, coronal mass ejections are a different story, but that's a story for another time. The health and safety of satellites are you know, there are issues with that, with coronal mass ejections and radiation storms. But that's, you know, that is very highly dependent upon orbit and the conditions and the CONOPS, you know, how the operations of the spacecraft is you know, been implemented, as well as the duration at which they're dealing with this. So, you know, space is not space, and every different orbit has a different environment. and it requires different type of engineering. So it's a non-trivial question to answer. I'd have to know a lot more specifics about, you know, which satellites you were interested in. Hopefully that answers that. Okay. Oh, did they not? Did they? They got a G4 watch. Good for them. I thought they were going to keep it. I looked at their what you call it, their 3-day thing for yesterday, and they had it at G2, and I'm just like, oh, you're kidding. I said, I'm not going to keep it at a G2. I'm going to at least raise it to a G3 with the chance of a G4. So I'm glad they have. I'm glad they've got a G4 watch on. I agree with that completely. That's something that they, you know, I'm glad they, and I don't think they'll ever put out, just so you know, I don't think they'll ever officially put out a G5 watch, because that makes everybody, you know, say, quick, fetch me my brown pants. And that's never a good thing. So they'll always put out a G4, even if they worry that there might be a chance for a G5. Do I think this one has the chance for a G5? Boy, I don't think so. I think we'll, if the worst it will probably be will be a high G4. I just don't think that we're in the right crosshairs for this to be a G5. And the main reason for that is if I go back to, let me where's a good, let me go to the beginning. Sorry if I'm making you dizzy. La la la. Boom. There's a good one, right? I was trying to get it right when it was flaring. Can I make you flare, please? There we go. There we go. The reason why is it's just so high. Okay, we're clear down here. So the bulk of the structure, no matter what, the bulk and the strongest part of the structure, the strongest part of the solar the shock wave, the strongest part of the flux rope structure, it's all going above us, whether we like it or not. I would love, you know, not necessarily would I love for this to be down here, but when we get these structures coming by us, I would love to have a spacecraft up here, like Solar Orbiter, that can actually see these things. But not only that, so that's one reason why I don't think it's going to be a G5. Another reason why I don't think it's going to be a G5 is that this same set of regions was firing on the far side of the sun for what, 2 weeks, basically. Came back around and is continuing to fire. So a lot of the material that, you know, that when you have a pristine environment, like the very first big storm that you launches a ton of material off the sun. All of that has been evacuated. So I just don't think these storms are going to be as dense as they otherwise would be if this were a newly emerging region. So that's why I'm not going to put out a G, you know, why I wouldn't say that this could reach a G5 level. I think a G4 watch is good. I think, you know, a G3 is, I think will absolutely hit G3, but I said with a chance of a G4. So that's why I say that, despite how beautiful, right, this eruption is and these other eruptions are. Hopefully that answers that question. Okay, planes aren't going to fall out of the sky. No, no. I know, I don't know why people, you know, they're so nervous about this stuff. It's like, guys, it's weather. It's just weather. It's not, you know, people want to talk about kill shots and extinction events, and it's just, this is not how this works. This is something that that technology doesn't like. But human beings themselves are, you know, we're pretty resilient creatures, and this just doesn't, our Earth protects us so much better than a lot of us want to believe. And yeah, okay, the collapsing magnetosphere, oh come on, it's only the dipole component. There are a bunch of other components of the Earth's magnetic system, okay? There's the quadrupole, the octopole, the even higher order terms that do protect us. Even when the dipole field goes to 0, we will still have an atmosphere, and the quadrupole field will still stand off the solar wind enough to protect the atmosphere. I mean, it's just crazy. You know, and okay, are there going to be more pickup ions? Okay, maybe a few. But are we going to miss them when they evaporate from the ocean? I don't think so. We're on a water planet, guys. We're okay. Seriously, it's not the end of the world. And the fact that so many people want to make it such, just, again, as I've said probably a million times, this solar cycle is underperforming. This solar cycle isn't even average, okay? Solar cycle 24 that most of you have lived in or lived before, and that's the only solar cycle that you knew, what you cut your teeth on, that solar cycle was anomalously low. That's not a normal solar cycle. That is when the sun literally hibernated its entire cycle. It did nothing. We kind of were flabbergasted. There wasn't even a G5, not once. I mean, it was like, whoa. So this cycle is finally getting back to a little bit of normalcy, but it's still underperforming. Something tells me that half of the people that watch these YouTube videos and watch social media anymore, if they had been alive back in the 50s and 60s, they would have had a heart attack, because the kind of solar cycles that we had back then were way stronger than anything we've seen here. We would have several G5s in a month, in a single month, let alone, you know, none per solar cycle. I mean, we'd get like, over the course of the busiest year, we had something like 4 or 5 solar G5s. It was easy. It was like, are you kidding? And the radio bursts and big radiation storms that we'd have. I mean, this is when we had big Carrington events actually hitting Earth. And look, we're still here. It didn't take society out. So please do not be afraid of these things. The space weather is just an inconvenience. And yeah, some of it is more inconvenient than others, depending upon your profession. But please do not think that this is going to send us back to the Dark Ages or do anything that is going to you know, cause some kind of political or geopolitical upheaval. It just isn't. It really isn't. Most of these things, like I said, are minor inconveniences. So anyway, I'll get off that soapbox here. Yeah, don't let people on YouTube scare you. There are people out there whose jobs are to scare us, and they're trying to make the end come. I'm so sorry, Paul. I know they're out there. Sadly, I've trained some of them, and I feel very guilty. If anyone's wondered why I have not done a mini course in a while, it's because of that. I've had to kind of come to grips with the fact that there are people learning from my mini courses who are turning it into nefarious, using it for nefarious purposes. Grifting, basically, and it's it really, you know, it hits my heartstrings hard, because I feel like I'm partly responsible for that. But other good people have told me that I also train good people, and those good people are fighting back, so I have to keep training. So yes, I will do another mini course, but it has really rocked me on my heels recently. Do I expect any earthquake increases? I expect earthquake increases every night around 1 a.m. in the morning until about 6 a.m. in the morning, because that's what happens. There's a diurnal variation in earthquakes, and everybody always seems to use them for, oh, look, it's space weather's fault. No, it isn't. We get earthquakes all the time. In fact, I've kept my earthquake monitor on my geochron so I could just watch how many there are, and there's been a ton of earthquakes, always, and they don't correlate with solar flares or big solar storms, because you can just cherry pick them, right? There's just so many of them, and sometimes, you know, the geographic complexity of the topology of a particular area is so crazy that earthquakes come in exactly the opposite times that in some other geographic location on Earth would cause earthquakes to come all the time. So like you'd have earthquakes here at this particular time in this particular way all the time, and you know, when under these conditions, and that's exactly the conditions that causes this area to go quiet. But the time that makes this area go crazy is exactly the kind of conditions that makes this area go quiet. So the geography and topography of Earth itself is so complex that in different parts of the world, right, earthquakes happen for different reasons at different times, and different things trigger them. So for people to say, oh, well, space weather just in general makes earthquakes go up, that's silly, because nothing in general makes earthquakes go up. Okay? It's always one particular thing, or one particular over here, or one particular thing over there that makes earthquakes go up. As I'm learning more and more about this, it's like, oh, wow, it's just like when people say, oh, well, space weather's going to hit, there's going to be Aurora. And you know, am I going to see Aurora? And the first question I ask is, where are you? Because it matters. The kind of space weather impact you get is dictated by where you are on the planet and what time it is. Seriously. You may not think that, but it's true. Space weather's not a global thing. It's just like weather, like terrestrial weather. If someone says, is it going to rain today? The first thing you ask is, well, where are you? Right? And what time is it there? Right? Because that's the way Earth is. Earthquakes are the same way. You can't have just a global, generality. That's oversimplifying the actual physics. The actual physics is it depends upon where you are, the particular stresses for that particular region, right? And what causes those stresses. And then also what time is it and where and what latitude are you in? And then maybe, once you get that figured out, then you can talk about, okay, will space weather happen for this region? Will it exacerbate an earthquake for this particular region? You can't just say, oh, ring of fire is going to light up. It doesn't work like that. So no, don't look at earthquakes and space weather as just so easily linked. And anybody who's telling you that is grifting. Once again, grifting, because it's so easy to do. It's just so easy to do because earthquakes happen all the time. So does space weather. So I can go, oh yeah, that happens with that. Look, see, they're causal. No, they're not. No, they're not. It's silly. Anyway, don't let people do that to you guys. You're too smart for this. So energy into the system has no effect. Of course it has an effect, but the effect is different depending upon where you are. Just inputting energy into something may actually drain the energy out of something else. Okay? It may actually liberate water underneath the soil and then cause that conductivity to change. And so as that leaks off, it reduces a potential for earthquakes, not increases. It's not simple. People say, oh, you just add 1 + 1 is 2 and it's perfect. It's like, no, because there's a scalar here and there's a factor here and this one's raised to the 7th power and this was an inverse relationship. See, the actual physics is much more complicated than just simple addition. Don't allow people to grift you that way. It's not easy, guys. Don't allow them to do that to you because then your heart rate raises and it makes you panic and then you start thinking that space weather is going to kill you. Please don't do that. Don't let them do that to you. It just breaks my heart. All right. Anyway, I'll get off my soapbox, but yeah, I just keep hearing this stuff all over. Don't let them do this to you guys. Okay? How does it affect the human body? Well, there are quite a few ways that happens, actually. And the medical industry is finally getting on top of this. Thank goodness they're beginning to really do some serious research into it. Now, do we know all the ways? Not really. The problem that we have is, just like I said before, space weather is so affected, or it's so different depending upon where you are, what type of space weather effect you're going to get, the type of biological implication or comorbidity you might have. So there's a ton of research being done on it right now. People are pulling out in some of these big, long databases. They're actually pulling out really strong correlations, statistically significant correlations. So the information is coming, but it's very, very difficult to to just, again, do a blanket statement because it just doesn't work like that. Different people, if you have metal, like for instance, if you have heavy metal poisoning, stuff like that, you have metal plates and screws in your head, you have devices that are affecting your electromagnetic, giving them electromagnetic pulses, TENS units, things like that. Those are very geomagnetic storm susceptible. However, other people who have implantable devices in them, they go up in planes. Big radiation storms like the one we're having now can be an issue for them. Okay, so again, it's non-trivial trying to figure out exactly what type of effect you're going to see biologically. And we need to let the medical industry work out those details and get funding to do that research, because it is becoming clear. You can even have a conversation with ChatGPT anymore, and it does recognize that there are mild effects that are notable in reputable journals. So, and again, we're putting together a database about it. We've got the database, we just haven't released it publicly, just because we're trying to figure out how to do that in the most ethical way. So, hang on, hang in there. We'll get that information out to you for pretty soon. Okay. All right. Yes, and I never make you pull money out of your wallet. No, I don't. I don't. So that's how you know I'm doing this because I love doing this, and I do this because I want everybody to have the right information. I am not trying to make money off of anyone. Okay. Let's see. Yeah, I hear you, Paul. I hear you. Okay. Guys, all right, so let's see. Shall we dive into some of the actual real stuff? Yeah? Yeah, and I see one turn. What, Sol Ren? Yeah, I hear you. He's not the only one who's at odds with me on earthquakes, and that's good for him. But I will tell you this, he's one of the ones who learned from my mini courses. So you take that where you will. Anyway, okay. Let's see if I can switch computers here so I can show you guys some cool stuff. Did that switch? Hang on. Maybe that will. Yep, good. Okay, so now I'm on this second system. All right. So the first thing, we're at Swipsy's webpage for just a second. What I want to show you guys is this radiation storm. So just in case you weren't aware, you've got multiple different colors here that are showing multiple different flux levels. So this red line, which is the highest, which is sitting at the S2 level right now, you can barely see that little line coming through here. This is an S2 radiation storm, and it looks like we're kind of popping down below the S1, or down below that line, down into the S1, a high level S1. That'll continue to go down for a little bit until that shock comes, and then it'll pop back up again. This is the one that I was talking about. This level here, this low level flux, this is the 500 MeV fluxes. This is half a GeV. This is like cosmic ray energies, okay? This is extremely energetic, and to see these flux levels so high, if you can see that little gray line right there, that little gray line is the S1 level for 100 MeV, which is this green line. The green line is way up here above the S1 level. That's what this dashed line is. This dashed line is the S1 radiation storm, official radiation storm threat level for the red line. And you're seeing 100 MeV, not 10 MeV. This is 10, this I think is 50. There's 100, there's 500. So the S1 level for 100 MeV particles is actually clear down here, and you're seeing 500 MeV, 5 times the energy, way above that level. So right now, astronauts are probably under their bunker, under the water storage, and dealing with flash, pinpricks and fireworks in their eyes, even with their eyes closed, because this is a very strong radiation storm. I seriously doubt you're going to see any EVAs. If they had any EVAs, I bet you they've been scrapped. This is one of the few times where you actually will see space weather really playing a role in astronaut activities. They oftentimes will go out and do things during mild space weather events, which drives us crazy, but they do it anyway, because they've just got a lot of other, there's so much that they have to do. They have to kind of deal with space weather. But this probably takes precedence, because this is pretty energetic stuff. And it means that there's a lot of things, a lot of the ISS itself and other spacecraft right now are really dealing with some pretty heavy impacts, possibly getting radioactive. Isn't that funny? Actually getting hot because of this stuff. This is what I worry about with us having people on Mars and the moon, is having big radiation storms like this, because you can't really shield. When you got 500 MeV, you can't really shield out of them very easily. Okay, so that's that. Let's take a look at, no. Okay, ooh, looks like we might be, ooh, guys, we might be about to get hit by this thing. Okay, so, put this on. For those of you who had asked about solar wind, let me take off BY. Okay. For those of you who have asked about solar wind, this is typical solar wind, right? This is a mess, all that turbulent junk. Okay, this is magnetic field up here. Okay, this is over the last 3 days, I believe. So here we're looking at, I hope you can see it. I'll make this big so you can see it. Or rather bigger, hopefully. Okay. So this is what, the 11th, oh, the 9th, right? So we got the 9th, the 10th, and the 11th. We're almost at the end of the 11th. Okay, you see that? It looks like that popping up. But you notice all this in the magnetic field is all ratty. All the different components are very ratty. We got a fast solar wind. We were in the high wind stream. This was our fast wind stream. This was at 600 kilometers a second coming on down. And it's really gotten slow, which I think is partly why we've seen some delay, is because now we're sitting down at around 400 kilometers a second. And yeah, and so this is, the slow wind, you've got to have that fast ICME slamming against the slow wind, and it's just going to hold it back a little bit. But notice how smooth suddenly the magnetic field got. For those of you who thought that, well, it looks like this might be a solar storm, you are right. But we are very clearly, I mean, it's not that this thing has lasted over a day because it's just, that's how big the structure is. It's actually because we are traveling right down the tube of the solar slinky core of one of these storms. So if you think of a solar slinky being a spring, okay, we are flying down the tube, down the leg, okay, one of these legs. If this is the sun, right, coming out like this, we are flying literally down this. It's hard for me to show it to you, isn't it? Let me grab my stick. Hold on. So if we have a solar slinky that's come out like this, I'll do it this way. Here. So imagine this is the sun up here, and it shot this big slinky. I'm going to use gravity to help me out. So this solar slinky is coming out this way. We are literally flying. We didn't hit this structure here. So my stick here, if this is the spacecraft trajectory, we didn't go through the center of it like this and go through it this way. We actually went through the leg. That's what we're going. We're flying literally down a leg right now. Okay? So that's why it looks so smooth. Okay? But it also, how do I know that it's a leg? Well, do you see this yellow line? As a matter of fact, I'll take this white line off for just a sec. See this yellow line? This is the X direction. It means it's the sunward to anti-sunward. It's the direction that goes either toward the sun or away from the sun. And in this case, it's going away from the sun. Oh, is that true? Wait. No, it's going toward the sun. Forget which coordinate system I'm in. So we're going toward the sun in this. And yeah, because it's a GSM. And notice that it's almost as big as the white field. The white field is the total field, so that's the total field strength. So this field is almost totally radial, meaning moving toward the sun. And that's exactly the direction that you get with the leg. Now, is it slightly, you still have a slight rotation? Sure, sure you do. But going down the leg means that rotation gets really stretched out and slow. And so that's what we're seeing. So that's how I know, and the BY component is basically 0. And that's how I know that we are actually going through the leg of a structure, is when I see really strong radial field. Okay, I'm actually going to use this for my SWEN students probably tomorrow. Really strong radial field over a long period of time. And when you see that and you see how low the variance is, meaning that the rattiness of the magnetic, look at the speed of the solar wind is really kind of getting soft. Then it gets really, you know, very smooth. What we call the variance goes way down. That also lets you know that you're in a strong magnetic structure. But look how slow it is, right? Sitting at 400 kilometers a second now. So this is, if you've got that big leg kind of in the way of another structure coming, that other structure is not going to just jump over it. It's not going to eat it and cannibalize it. It's going to sit there and wait. It's going to slam up against it, pancake against it, and wait for it to reach Earth. And sure enough, that's what's happened. Because do you see this? Look at this, guys. We are literally seeing the solar storm hit right now. Zoom into 6 hours. Wahoo! Here we go. Everything's popping up. So it finally popped out of the leg, and it looks like that solar storm is hitting us right around 2200 hours, which is what we expected from solar orbiter data. Okay, so, and look, strongly southward. So we'll see what that's the sheath. We'll see what we've got here. We're not seeing a strong shock yet. So this may be stuff in the front. This may be the back end of that other CME, that other ICME. We'll see. We'll just have to see with more stuff coming in what ends up happening. But it's interesting to see strongly southward. That's Aurora photographers are going, come on, sunset. But yeah, we're probably seeing a little bit in. That might have even triggered a substorm. So if other folks are here, they probably will, like Vince Ledvina, if he happens to be in, he'll let you know. Let's see. What was I going to do? Oh, I was going to show solar orbiter data. Yeah, so here's, let me reload. So solar orbiter magnetometer data is definitely showing wahoo. So here's the total field. Whoop. Not for publication. Hopefully it's okay for YouTube. So normal solar wind, because solar orbiter is inside of Earth a bit right now, so normal solar wind is a little bit higher than what we see at Earth, or at L1 rather. But look at this jump, up to 30, almost 35, 32 to 35 nanotesla. Definitely got some sheath material. This is a strong shock. Looking at, so this is 12 hours. Yeah, so really squished a lot of time in here. But that looks like a good shock right there. It's in a slightly different coordinate system, so don't freak out when you see stuff that doesn't look exactly the same as what we see at Earth. Plus it's rotated around a little, I think, so it'll see something different anyway. So don't try to correlate unless you know what you're doing, don't try to correlate what you see in the components, the magnetic components of solar orbiter with what you see at Earth, because it will be different. All right. Yeah, you're still seeing, and it's transverse, so it looks like, yeah, it looks like it's hitting it pretty well. I'm looking at the 30 nanotesla here, looking at minus 25 nanotesla here. You want the components in here. You don't really want the components to be radial. So it's good that we see less strong components that are radial. Because that means that it is going through the solar slinky core. So there's a good chance that it will see that slinky core, which is what we'd expect because solar orbiter is at higher latitude than Earth, which I can show in the 3D visualizer here in a minute. But yeah, this happened, shortly after, sometime this afternoon. So it makes sense that we're seeing it now. That was I think Glenn Wheatley who actually did the calculation and said, yeah, seems like it'll be on time for an Earth hit if it arrives around 2200. So sure enough, that's what we're seeing. It's 2230, and we are getting something. So this is a good sign. This also is a really good sign if we end up getting a decent hit with this one. If we end up getting inside the solar slinky core, I think it will end up being even better for the one that's coming on the second storm that's coming. I think that'll be even a better hit. Okay, so just be aware. I don't think we've seen the end of this yet. 500 kilometers a second. That's pretty slow. I think there's a good chance. I think there's a good chance that it will speed up. Okay, so that's what I wanted to show there. And now let's see. Let me go ahead and do the fun stuff here. So. Okay, I've got two of them. I'm going to pull this down. Let me pull up. Where is Safari? There you are. Okay. So speaking of, let's talk about that first rope. So this is the Flux rope visualizer, and I'll probably put after this thing is over, the live feed is over, I'll probably put a link to the live version of it. Otherwise, if you happen to be in Patreon and you can get access to the Welcome Lounge, you can go and take a look at the links there, because all of my analysis is there. But this is the Flux rope visualizer live. I'm manipulating it on just by using the mouse. This is for the 9th, I believe. Is this the 9th? Oh no, hang on. Let me get to the one that's the 9th. And it is an animation. So what's cool about that is that if I kind of just set it at some random angle and I hit play, oh, it wants to play. I'm sorry, it's on a Mac, so there it goes, it's playing. I think it's playing, yeah. It's on an old Mac, so it's behaving rather strangely. Now, you can get this to play starting from scratch all the way out. You can manipulate the little sliders on your own. And the only problem that you have is that you have to hit pause. You have play and pause buttons here, play and pause. You have to hit pause if you want to manipulate it. There we go. And pardon my old Mac as it struggles. Why are you having so much trouble? You were doing fine before. Wonder why it's struggling so much now. Maybe because it's displaying it. That's probably why. My poor Mac is going, it's having trouble. Make sure I put this on rotation, turnwise rotation. And come on, rotate right. Wow, it just wants to do it backwards. I'm not really sure what's going on. Am I doing it? Okay, that's why. It got flipped upside down. How strange. Okay, now we can do this better. So this is the structure. Let me zoom. Try to get out of the way. So this is the structure. Oh, man, why do you do this to me? I don't know. This is the structure, if I can get it to walk all the way around so you can see Earth over here on this side. Okay, there's the sun. So you're looking at this from the west limb, or the east limb of the sun. Right, so this is the east side, so solar storms go off to the east this way. And then I'm going to rotate Earth around in front. If I can do it gently. And this structure hasn't reached Earth yet in this, or in the frame that I've stopped it in. I'll get out of the way. So you can see there's Earth. Here's stereo A, so you can see it from stereo A's perspective as well. So what I did in the actual analysis was that I actually got the structure lined up with the sun and stereo, like this, pretty close to this. So here's stereo A looking straight down the pike toward the sun. And I looked at this way that this structure looked relative to the coronagraphs, and I can put that up in a sec, and tried to get the fine features. So the shock wave, the way the shock wave had this indentation out here, it lined up with this kind of leg coming out this way. If I had the structure tilted this way, there were some fine features in here with some oblong circle shapes that worked well if I tilted the structure like this. And then I turned around and I did the same thing at SOHO, at Earth, and lined up everything I could. And between the two of them, keeping it within this gold lemniscate that NASA created, I tweaked empirically the flux rope structure inside that lemniscate to get the solution I got. Okay, and I'll show you the coronagraphs in a sec. But what I wanted to do right now was just kind of see, and I just touched that, and it goes wonky on me. It never used to be like that. Sorry, guys, I don't know why. I will, like I said, I will give you the links so that. All right, let me see if I hit play. What are you doing? You're looking at it from underneath. I know that because stereo A is on the wrong side. Well, I had no idea it was going to be this weird. It doesn't do this normally. It's just because I'm trying to present. All right, let me see if I can park it. So this is a similar view. Maybe I can just touch over here and hit play. Cross your fingers. Nope. There, okay, it came back. I don't know. Don't ask me. Okay, so this is Earth here. There's stereo A. But as you can see, Earth is kind of going to go underneath this structure mainly. So I'm expecting that we're going to see it just through the envelope, which is what I showed at in the forecast, the official forecast. But now I'm so gun shy now to try to manipulate anything because it's so strange. Go back. Okay. All right, so yep, as soon as I touch it, it just goes wherever it wants to go. Okay, now I'm going to line it back up to the sun. There, so there's Earth and the sun, I believe. Earth and the sun together. Now let's see if I can play it one more time. Go back. Okay, it just flips and then comes back. I have no idea why. Okay, so there is the view from Earth, right? So this is why I believe it's going to be something where we're not going to see the legs of the structure, but solar orbiter, if you notice, here's solar orbiter way up here. So I would expect solar orbiter to see this, okay, because it is so much higher than we are. Let me see if I can pause and pull this back down because you are being such a pain in the tush. Hold on while I get it oriented. There, from the side. Okay. Here's the sun. Here's stereo A. Earth is slightly behind it along this ecliptic plane. Solar orbiter is way off the ecliptic plane. Look how high off the ecliptic plane it is. So it will actually go through the actual loop of this thing where Earth will go underneath it. Okay. Now, let me flip to the next one. This is the one that's going to be hitting us on the 10th. I mean, this is the one that was launched on the 10th. And let's pray this thing behaves a little bit better. Okay, so here is this one lined up with Earth. And I'll hit play. Yeah, this one's actually behaving better. Okay, here's Earth, and you can see this one much more low angle here. Again, the shape of this thing had to do with the shock wave that comes out, and I will show it to you here in a second. But the lemniscate is basically NASA's lemniscate. I shrank it a little bit so that I could see the legs a bit more and be able to work with the shock a bit more. And that becomes apparent when you look at stereo A. The lemniscate is just a little bit tinier than it should be. But it made it easier for me to see the envelope, and I had to do these kind of quickly because they're so back to back. But you see how Earth is going through this. We're really just grazing the hairy edge of this thing, and that's if there's no distortion. And I expect there to be some distortion pancaking. So the chances of us seeing the actual tube of the second one, the actual solar slinky core of the second one, will be very, very high. Now, regarding the third one, well, to me it looks like the third one may be very much like the first. Okay, much more highly tilted. But I haven't had a chance to actually do that analysis yet. So let me show you, for example, how, now that you've seen those lemniscates, here is what I'm talking about. When I talk about the fit for these things. So this is, okay, here's Earth, right? I put it right. This is SOHO. This is the view of the coronagraph at SOHO for that very first solar storm launch. And what I used in the SOHO coronagraph is I used the angle here of this structure. You can see this structure kind of out like this. And I used that axis of symmetry to guide the, a preliminary idea of the fit. And you can actually see even some of this kind of stuff, and this is the worst of all of the fits, by the way. I don't really like it all that well, but it was the best I could do, especially given the other constraints. You can see it come out like this. The lemniscate caught most of this stuff up here, okay, but there's this thing, and so you have this elbow that comes out. So that's what I used in the SOHO to constrain the orientation of the lemniscate. I mean, the orientation of the flux rope structure. And then if I go to stereo, this is that same, using the same parameters, so the same exact fit. This is now the view from stereo. So you can see it with stereo, I've lined it up with the sun right there. So this is the coronagraph image that you see right there of stereo, and now I'm overlaying that lemniscate with the same parameters. So you can see, again, it's a little bit, the lemniscate needed to be a little bit bigger, a little bit wider. That was my fault. But you can actually see, there's a, if I can show it in here, you can see an actual kind of curve where most of the material is in this, the brightest part of this thing. You can see part of this tube coming down this way. It actually almost looks like a heart, and I've done this in the past, where it almost looks like there are two tubes. There's a kind of a cavity here and a cavity here. And so if I were to draw an outline, it would almost make like a heart shape, right here and right here. And those two cavities are the two legs of the structure. So I tried to make sure that the leg of the flux rope on one and the leg of the flux rope on the other went through those two cavities, while still maintaining all the parameters on the SOHO view, right? And still maintaining the confines of the lemniscate. So it was like, this was probably the hardest one to do because it was such a ugly coronagraph eruption. But that's why I think this one is going to be more highly tilted. It's really stereo's view that gave me that real sense of it because, believe it or not, of these two tubes. See how this cuts in? There's like these two tubes right here, if I can put my hands on them. And those oftentimes end up being the legs, the way if you can think of a flux rope being like a, think of a flux rope that's like a transparent jellyfish, and like seeing it underwater as the sun glints off it. You can kind of see through it, but there are certain parts of it that get thicker. Yeah, it's kind of like trying to do something like that. So this was ratty. The best I could do to try to get those fits to look anything like what we see in the coronagraphs. The next one was much, much easier. This is the coronagraph from from Soho. So this is the Earth view. This one was much, much easier. Again, we got that shock coming out on this side, but it was really kind of asymmetric, if you notice. Really wants to come out on this side. And then you've got this long, elongated structure in here that comes out even further than this stuff does. Notice this thing comes way out here when you look at just the coronagraph. So I used that to help constrain what this potential shape could be. Okay, so that was how I did it at Soho. And then using these same parameters, and you can see here even the loops sticking out. See this? It looks kind of like a loopy thing. And then it kind of got a little bit of a loopy thing up here, but it's kind of bent a little bit, which is very similar to the way we saw that in the off the sun itself. Okay, so coronagraphs are really hard. This is why I put this in the deep dive and not in the main gist of it. Okay, so with these same parameters then, I turned around and I did the stereo lemniscate. And this is where the shock wave really came into play. Look at this shock wave. It's really, really high and it tapers to an edge here. Okay, and that tells me that there's a leg or something out here. It's shocking around a structure that's sticking out on this side. But you can see that shock wave, the edge of that shock wave. So I knew I needed to have something like that where this leg would pop out over here to keep that symmetry of the shock wave. Okay, so that's one thing. And then what also got me was this, there's a circular thing going on in here. Can you see this curvy, get this loop off. See this right here, it's kind of circular. It's kind of right in here. And so, and you can even see down in here, it's kind of curvy, right in here. Right up in here, all in through there. So that is what guided me for that. So between the shock wave, between the front of this stuff, it wanted to go, you know, wants to be a little bit higher than the actual structure itself. But between Soho and stereo and the two coronagraphs, this was the best fit I could get. And I did try to put a higher tilt on the structure so that it was consistent with the one that we saw on the 9th. I tried. Didn't work. Made everything get all weird looking. And it was, the leg was sticking out weird way, and this was tilted weird, and it just didn't look anything like the features, the fine scale structure here at all. So these were the best I could do, and we shall see, right? I mean, this is just an experiment, but we shall see how well it proves in the end, because a lot of these structures, as you know, they really, you know, they distort in the solar wind. The one nice thing we have is that when they're big and fast, right, they're typically magnetically strong when they come from regions really shot out of a howitzer like these structures were, from really explosive, really strongly eruptive solar flares. When they come out of those types of regions in that kind of environment, they tend to be very strong magnetically, and therefore they do not distort very much. They just kind of plow over everything and just really force everything to bend to its will. Everything distorts around it. So that's one nice thing, is that with these stronger structures, the chance that they will be distorted less in the solar wind is better than if they were weak, right? Stealth CMEs, I would never try this with a stealth CME because the thing, who knows what it's going to look like by the time it reaches us. And these didn't look like they were cartwheeling. Sometimes these eruptions look like they're rotating even as they leave the sun. And those are harder to get to. But these structures looked, you know, reasonably solid as they, you know, reasonably steady as they moved outward from the sun. So again, we'll see, right? Take it with a grain of salt, but it's a fun exercise, and we'll see whether or not that gives us something. And if it does, then what that means is that the first storm that we're going to see will either be strongly southward or strongly northward, right? And you'll get a solid period of time where it's that, and it'll be more closer. It ended up, well, I want to say it's going to be closer to the center, but it'll be a single period of time in that structure where you'll see that southward field or that northward field. And yes, that means that it could be a fizzle right away, right? Because if it could be all northward, and then when that's all you get. But the second storm being a lower inclination structure, what you will see is either it will lead with northward field and trail with southward field, or it will lead with southward field or trail with northward field. So either way, you'll get a flip of either a northward and then a southward turning, or it starts with southward field in the front of the rope and it flips to northward at the tail end. Okay, so that's one good thing about ropes like this, is that you always will get a piece that has some type of you know, aurora-inducing magnetic field direction. If it doesn't bend and twist and writhe. Again, take it with a grain of salt, right? So, okay. So hopefully that's interesting. And then there's one other thing I could show you real fast. As Andy Smith recognized in the ULU monitor, the ULU cosmic ray monitor, we finally, for the first time in ages, got a GLE. For those of you who do not know what a GLE is, it is a ground level event, meaning that we actually got an increase in cosmic ray flux instead of a typical decrease. We typically get a decrease in cosmic ray flux when big solar storms come by, because these are Forbush decreases, which, by the way, see that? See that Forbush decrease? This one that goes way down? I will bet you this is the storm that caused the legs that we have been in for quite some time. The storm didn't hit us except for the legs. And so the legs have been passing over us just for the last day or so, right? Last, you know, partial of a day. But this is either a single storm, or that's a long, God, those are days, am I correct? Last 30 days, oh my goodness, yeah. So this is a set of storms. So we've had a barrage of storms from region, you know, 42, 72 and 74. A barrage of storms from them. But that's what we're in right now, is the storms that have basically missed Earth, but they were still close enough to Earth to give us a nice Forbush decrease. But this big, way big jump, that's from those really energetic particles from this solar energetic particle event. We had particles reaching all the way to the ground. Yeah. So this was pretty intense. Neutron monitors are really good at picking up really high energy particles because they're looking for that exactly. I mean, they're looking for cosmic ray energy particles. So that's what they're seeing. So they're seeing cosmic ray showers from this solar energetic particle event. And they don't last long because the high energy stuff just disappears pretty quickly. Stuff doesn't penetrate in our atmosphere very, you have to have really high fluxes to be able to see this stuff. And the fluxes die down too quickly for it to reach all the way to the ground and at least make a noticeable increase in the neutron monitor count. But it means that there's been a lot of cosmic ray showers in the upper atmosphere over the last hour or two. Very, very, very energetic radiation storm we're in right now. This may be the first GLE we've seen in this entire solar cycle. I don't think we saw a GLE at all in solar cycle 24, not a single one. So this is a pretty landmark event, okay, if for no other reason than simply because of the GLE. And again, is that the end of the world? No, it really isn't. It causes big radiation storms, but that's not the end of the world. It causes issues for avionics and aircraft, but they know how to deal with it, right? They've been, we've flown through, many people have, and what the FAA does and what the other agencies do with airlines is that they divert them away from the poles, get them away from those radiation storms, because if you fly at lower latitudes and lower altitudes, you completely avoid that because you let the atmosphere absorb it all so that you don't have to sit there and deal with that particulate radiation. What does that mean? Well, it means they spend more fuel. What does it mean? It's actually a boon, because it means that people don't have to get irradiated quite so much. It keeps the planes safer, it keeps people safer, and it does spend more fuel, and it may make the flight longer, but it's definitely worth doing that to keep people safe. But yeah, so that's what's going on, guys. And I'll go back to the real-time data so that we can see more of this solar storm unfolding. And let me actually go ahead and check, as you can see that, whoop, you can see that storm unfolding now. Let me go ahead and check some Patreon stuff. Let me take a look in the chat, see if we have some good stuff in the chat. Tim Gunn says you're going to be flying when the storms hit. I'm so sorry, Tim. Oh my goodness. You'll be bringing your gamma spectrometer with you. That's so cool. Oh, right on. Please share the data. We gotta just wear a lead apron or something. Mary Beth, oh, she's so excited for this stuff. And Frederick, oh, thanks. Thanks, Frederick. I appreciate it. Let me see if there's other, let me go back to the real-time stuff. Let me see if there's anyone else who wants to ask a question on Patreon on the comment section. And then I'll get to you guys, because there's usually maybe one or two, or sometimes none. Sometimes, because most of the time you guys are with us here. So if I can get to, let me get to my posts here. Load more comments, let's see. Okay. Okay, cool. Yeah, some people are not seeing didn't see the feed from earlier. Oh, can't believe that happened. Glad you guys were all able to catch it. Yeah, look at this. So those of you who are looking at the red line, by the way, which is the magnetic, the north-south component of the magnetic field, pay attention to this, this blue field too. This is the Y component. Believe it or not, Y component can drive Aurora, definitely substorms. So, because it increases what we call the crosstail current. So just because you don't see a lot of strong magnetic field that's north-south does not mean we won't get Aurora. So this is a good start. Let's hope that the strength of the storm increases, but I think it will. What I'm surprised about is that we really didn't see much of a shock, at least not yet. And that's another thing to check real fast. Let me reload this to see what our super thermals are doing. Oh, it's still climbing. Let's see. There's a little bit of a dip, but they're still climbing. So the shocks are still coming, guys. Okay. So you can see it here. Shocks are still coming. Let me take a look at the last couple hours. You might see a little bit of a dip. No, it's plateauing a little bit the last couple minutes or so, but I think you'll see it plateau and then it'll rise again. These super thermals, for those people who chase super thermals, they are a good way of looking to see whether or not a shock is coming. Once you're inside, especially during a radiation storm, once you're inside a solar storm container, okay, a magnetic container, these fluxes will stay high and they'll just kind of ride up and down and up and down and up and down until the last shock passes, and then they'll begin to die because the shocks behind them are feeding more particles into the container. So expect that this is going to be a little bit hard to read, especially because we have a radiation storm and we're also dealing with shock accelerated particles. But it still should give you a little information. Just don't bank on it because it could be a bit tough. And let me see what AE is doing. Oh, wait, that's right. I was going to do one other thing. For those who really want to know, if we go to the magnetometer, you might as well see. Yeah, we're just past noon. And don't really have much of a bump there. There's a bump. I was waiting for that. There it is. So yes, we are getting a bit of response from Earth already. So right now Earth is getting compressed. I don't think it's going to be enough to drive goes into the magnetosheath, but as you can see, we're definitely feeling it at geosynchronous. Earth's shield is getting crushed right now, compressed, and that's what's causing this big bump. I don't think these are substorms, guys. I think this is a compression. But only time will tell. And then the other thing is, let's see, let me go to electrons. Let's see if we're getting flushed. Not yet. Not yet. So this is the electron, I'll make it big here. This is the electron, 2 MeV electron flux. Also it goes, typically it goes up, down, up, down, up, down until it gets flushed during some kind of storm, which is what we've had, this is the last week or so. We got flushed during a fast solar wind, and then the particles slowly rise again, and then you start seeing that diurnal variation up and down because the satellites are going around and around. The day side is always more fluxes, the night side there's always less, up and down, up and down. And they continue to build. Okay, so these are energetic, this radiation belt flux is building up. And then what I'm expecting to see is a big flush, not seeing it yet. So we'll see what happens. We haven't gotten, we're just beginning to see the compression of the Earth's magnetic system. If this flushes then you know, we'll know that we're going to be start building up again. And I do think by looking at this, we're somewhat preconditioned, because as you can see, they were beginning to get up above that threshold. This is the warning threshold for satellite operators in GEO to worry about single event effects and, well, really spacecraft charging more than anything, but single event effects too. And so they have to worry about this stuff as these particles, as they pass noon. That's what the N means. The M means midnight, the N means noon. 2 spacecraft passing through noon is when the particles peak, then they go back down. But as you see these particles build up, it gives you a sense of how preconditioned Earth is. The more particles that are built up, the more preconditioned we are. And right now I'd say I thought we'd be more preconditioned, but I guess this recent flush from the fast solar wind really dumped us down. We do have some moderate level of material that mass loads the Earth, but it's not that big yet. So maybe we're not as preconditioned as I thought we were. But for what it's worth, for those people who understand preconditioning, when the Earth is preconditioned, it means it wants to storm, and so it's sometimes you can get just a hair trigger and it'll storm quickly. So that's what we're looking for. But I'm not exactly sure it's going to storm that quickly. We shall see. It may take a little bit more to hit up. So I don't know. Yeah, we'll just have to see how the storm hits. And let me just look to see what HP 30 is telling us. HP 30 is not even reacting yet. So if the GOES magnetometer isn't really reacting, I mean, it's just barely getting squished, it makes sense that the HP 30, it's way too early to get anything from HP 30 yet. So anyway, so we just got to keep our eyes on the solar wind and see what happens. Okay. All right. Oh, Control R is refresh. Thank you, Toby. I appreciate that. I didn't know. Okay. So any other questions, guys? I've answered a few. I got on my soapbox for a little while. Thanks for indulging. But you know, hopefully I answered some questions and gave you a good sense, and hopefully I calmed some folks down who were you know, really concerned about, you know, the kill shot, or you know, that everything's gonna start vibrating and, you know, we're all gonna transform into some, you know, unrecognizable state. It's not gonna happen, right? It's just space weather. It's just weather. You make this sound so interesting. Oh, I'm so glad you liked it, Paul. That makes me feel good. I'm glad it helped. No Aurora response yet from the shock. Yeah, bummer. Hopefully you'll get something soon. Yeah, because it's nighttime over there, isn't it? Right. Oh, you're right in the right perfect place for this. So Adrian, yeah, you even from that BY component here, you should get something here soon. Okay, so you should get something. But yeah, if it's not real preconditioned, might take a little while to build up, which is a kind of a bummer. Can you show on the Slinky what a flux rope is real quick? Sure, sure. So a flux rope, right, is and I love Slinkies. Slinkies are everywhere in space, in heliophysics, really. Space plasma physics or heliophysics. They're on the sun, they're at Earth. They're even what Earth shoots down its own magnetotail, believe it or not. And we call them plasmoids. And the reason why they're ubiquitous is because they're actually a very relaxed state. Magnetic field likes to be like this. And it doesn't like to just be coiled. It likes to be this plus this, which seems really odd, you know, if from this perspective. How does it like to be both at the same time? Well, if you take magnetic field that's all just straight, let's say just straight up and down, like this, I'll stand over here, like this, I wish I had a black screen. I usually have my iPad with me, but I know what I'll do. Well, no, I won't. I'll just stay here for a second. Okay. If you have magnetic field that is just straight up and down, and let's say you have a lot of them, a lot of different lines of magnetic field going just straight up and down, what ends up happening is that it just like when you have two magnets and you push them together, if they are all facing the same direction, meaning North Pole up here, South Pole here, or if you reverse them, South Pole's up here, North Pole's here, so I'd have my finger pointed this way, right? If you have a bunch of magnetic field pointing in the same direction, all right next to each other, just like two magnets that are the same polarity, you push them together, they repel, okay? They push away from each other. So imagine having a bunch of magnetic field, just like this, all stacked really close to each other. They are all pushing out. They're pushing out away from each other, right? What we call radially outward from their center. Okay, so if you had a bundle of them, there'd be force pushing outward. Okay. If you have magnetic field and you coil it like this, okay, round and round and round and round and round, that magnetic field wants to collapse. It wants to crush in. So its magnetic pressure is pushing all the way in. Here's the cool thing. If you stick a bundle of magnetic field pointing up, you know, all in one direction, inside a set of coiled magnetic fields, you can get something called pressure balance, magnetic pressure balance. The magnetic field that's all pointing the same direction is pushing out radially, while the magnetic field from the coil is pushing in radially. So suddenly you can make that perfectly balanced so that everybody's happy. There ends up being no force at all. So we call that kind of state, that's called a Taylor state in this case, we call it relaxed. So a flux rope structure is a structure that is coiled, coiled, coiled on the outside tightly, and straight, straight, straight on the inside. And in between, going from the inside to the outside, it's a slow transition. So you go from being being no coil to just slightly coiled to tighter kinks and tighter kinks and tighter kinks until you get to the very outside when everything is really kinky. Just kidding. But it's really tightly coiled, okay? So what I mean by like a loose coil would be like this, where I stretch the slinky out. See how loose that coil is? That would be on the inside. And then you go further out, the coils would be tighter. And then you go further out, and the coils are tighter. Get it? Until you get to the very edge, and it's pretty tight. Not super tight, but tight enough. And so that's really what a flux rope structure is. And if you modulate and moderate and shift and change the magnetic field configuration just a little bit, you can end up getting into a pressure balance. And that's what these flux rope structures try to do automatically. As they expand out in the solar wind, yeah, they're getting bent and the magnetic field has to curve and coil and stuff like that. But inside itself, it tries to relax into what we call that Taylor state. Okay? And that Taylor state is actually mathematically described by a Bessel function, locally at least, that's straight. But then you curve it into what I've done with the flux rope visualizer, for example. Right, if I pull that back up again, if I can, without it getting all weird on me. Okay. Pull it back a little bit more. Hopefully, I don't know if you can see that very well. Let me see if I can tilt it. There we go. Don't move. Okay. So in this case, I've taken this slinky, right? If you can see my black, guiding, what I call the center line, it's like a guiding center, okay? But it's a line. So it's guiding the center of this flux rope. And of course I have to fight gravity. This cute little blue one doesn't. But if you take that slinky and you put it like this, and I take that black line, and I make that black line be this gold line, I can bend this structure. And right? And so the black line, which is that guiding center line, it actually bends back to the sun like a dipole field. It's very similar to a dipole field line. Now it gets stretched and squished and all that kind of stuff because the solar wind forces it to. The solar wind is actually filled with a bunch of particles and magnetic fields and electric fields. I call it a spider web because it really is like a web. I mean, the particles don't touch each other, but they're all connected by this web. And so this web really dictates how this structure moves and bends and stuff like that. But if you can imagine that slinky with that center line being in there, that's what a flux rope looks like. And that's what I've drawn here. Can you see? And I've only drawn a couple of the coiled lines, but I could draw a whole bunch of them. If I made it too complicated, you wouldn't see it. But it's essentially a slinky threaded by a center line string, a dipole field line string. That's what I've created there. Okay. And yes, it's an approximation. If you saw real flux ropes, there are papers on real flux ropes. Trying to think, a couple of the authors, Ruffalo et al., I think, did one recently that actually showed, you know, a flux rope structure that's all like all bent and writhing in the solar wind, and it's actually pretty cool. Those who were at the Space Weather Week in Europe recently got to see Erica Palmerio get a nice award talking about having to do the 3D characterization of these structures out in the solar wind, because they do, you can't just look at them at the sun. It's really a process as they go out, and their transit from sun to mud makes a huge difference in terms of their geoeffectiveness. So, you know, me doing this, obviously, I'm doing this more to visualize, because I want people to understand that what you're looking at in NLOL is not just a blob that cannibalizes other blobs. It's an actual flux rope structure. And eventually I'll make this twist and writhe and do some of that other stuff. But there's a lot of physics that goes into that. This was easy, right? That other stuff's quite a bit harder. And not something that we can easily do in real time. But hopefully that gives you a sense as to why there's so many flux ropes, and why do solar storms always look this way? It's because it's actually a natural state for it to be. Because if it can get into pressure balance, right, if it can get into this, what we call a force-free state, that means that there's no forces on it. And for those who are interested in how does it work, how does that happen, all you have to do is get the electric field to run in the same direction as the magnetic field. In other words, the magnetic field and electric fields are parallel. If you can do that, then the electric field cannot exert a force on the magnetic field, and the magnetic field is safe. It's like, I'm happy. No one's pushing on me, no one's poking on me, no one's making me change. And so these flux ropes fight to get to that state. They try to relax because the electric field is moving them around. And once the electric field can't move them around, oh, they stop, right? They're relaxed. They don't have to move and change anymore. So that's what a force-free state is. Incidentally, it's also the same thing as a potential field source surface model. That potential field is a field that has electric fields that are running the same direction as the magnetic fields. It's force-free. So it's the most relaxed state of the sun magnetically. And we can analytically state what that is using, well, we numerically solve for it, so it's not analytical because most of the time it's a mess, but there is a way to describe that. And so do we think that the sun is actually always relaxed? No, it's never relaxed. Do we think these structures are always relaxed? No. But they're always trying to get to that state. So that's why we use them to approximate what the sun looks like magnetically, or what this flux rope looks like magnetically, is because they're always trying to relax to this state, even though they never quite get there. Right? There's things force pushed on them all the time. So hopefully, did that help? That little, me playing with a little slinky. It's not just a toy. Yeah, slinky's a good analogy. Yeah, they're very useful. Whoops, how many degrees should I missed that. I'm seeing comments going up on the top. Okay. G4 possible, G5. Again, I don't know. I just don't think a G5 is possible. I think a G4 will be the best we'll get out of this. We shall see. We shall see. Won't be as strong as the Gannon storm. Anyone wondering what the Gannon storm was? That was a storm named after Jen Gannon, because she was a heliophysicist who we all loved and adored, and she passed just a few days before the May 10th event hit in 2024. That was the only G5 we've had in more than a solar cycle. KP index is low. It's not, we don't have time. It hasn't had a chance to really respond yet. And Earth is the solar wind is really underwhelming at the moment. The speed, right? The speed is really slow. So let me look at this again. Come on, the speed's at 493 kilometers a second. I'm not even completely sure we're completely out of the other structure yet. That's what I'm wondering if it's getting, because we just didn't see a very pretty shock. This is I'm not even sure this is a shock. It really doesn't look like it. So to me, this may be the tail end of the other flux rope structure, where they're still pushing against the legs of it. So don't expect that this is going to be all we get to see. I think there's more intensity coming. But remember, like I said, that first solar storm, I think the best that we're going to see of that first solar storm is the envelope anyway. I really don't think that's the best of the litter, so to speak. I think the second one is the better of the bunch, simply because its orientation is more conducive. At least its orientation as it came off of the sun was more, and in coronagraphs, out to 30 solar radii. Yeah. I think of it in sun lengths as well as radii, so I had to make sure I said the right words. Out to 30 solar radii, it looked like that. So, you know, I think there's a good chance that it's going to be more low inclination, that second structure. And so we probably will get a better hit from that. Have I been wrong before? Oh, how many times have I been wrong? I can't tell you I can't even count how many times I've been wrong. So, you know, it is what it is. No, I'm not drinking moonshine, just water. I know I drink out of a mason jar, so it's pretty funny. Okay. I've seen people talk about the flux rope during previous storms and had no idea what it was. My mind went too far off, but it never took into account the eruption's legs. Oh, yeah. So I'm hoping, are you guys liking the visualizer then? Is it really helping? I mean, like I said, I'll give you links. I'll put the links in the description, I promise. Because I think we have a server that's robust enough that can handle. Because this animation is not a small file. This will take probably a minute to load on your browser. The animation is probably, because it's all contained, it's all self-contained. The animation is probably 180 to 200 megabytes. So it's all contained in the browser. So when you click on the link, it'll sit there and for, you know, some people can load it up in 30 seconds, some people can load it up in 2 minutes. But it contains every frame, and they're like, I don't know, 50 frames or something. But it really does help when it comes to looking at something in 3 dimensions and getting an idea as to how the limniscate, which is the envelope, right, really doesn't give you the full picture of what it is you're seeing. And when you're allowed to play with it yourself in 3 dimensions, it sure is a lot more telling, right? This probably, even just me doing this live, probably looks a lot more like you can actually see it in 3D a lot better, you know. But it tells you how complicated these structures are and how wild they look depending upon your orientation. I mean, this has been the bane of space weather forecasters' existence, and even academic, you know, ICME and CME scientists for decades. Just ask Emily Kapula or Chris Mostel, myself, Russ Howard. I mean, I could Nat Gopalswamy. I could go on and on and on and on. You know, Erica, right? John Linker. You know, everybody from predictive science, basically. Pete Riley. You just go on and on and on talking about them all. And I'm sorry if I left their names out. You know, I've got lots of colleagues, and I'm sorry if I've left your name out because there's a lot of people. I didn't do it on purpose. Those were the names that came to mind first. So, okay. Any other big questions, guys? Oh, the Russell-McFerrin effect, right? Not McPherson, McFerrin. I actually know Bob McFerrin. He actually helped. He was Chris Russell was my thesis advisor. Bob McFerrin was just down the hall. And that was Paul O'Brien's thesis advisor. Very good substorm guy, very funny. Anyway, the Russell-McFerrin effect was a paper written in 1973 by Bob McFerrin and Chris Russell. I will out Chris and say that it was actually Bob's idea. Chris just wrote it up first. So Chris got top billing. There you go, Bob, I vindicated you. The issue there is they recognized early on that because the Earth's magnetic field wobbled, as the Earth rotates, it wobbles, that it tilts a certain way and it handshakes with Earth's or with the Sun's magnetic field in a particular way. So that during the equinoxes, we end up getting a stronger effect because part of the radio field that was coming out actually looked either southward or northward to Earth. And so it coupled into that component. So during equinoxes, we end up getting a stronger, storms are stronger than they would be at the solstices. So we're kind of moving away from the strong period, getting closer to the solstice. So I don't think the Russell-McFerrin effect is going to play much of a role here. It is not the only effect. There are others. I still argue that it's the strongest because it's the one I've seen be the strongest. There is also one that actually has a diurnal, also has a seasonal effect, but it's a different seasonal effect, and it also has a more of a diurnal effect. And yeah, it plays a role. I've seen the effect, but it's where I see it strongest is the Russell-McFerrin effect in solar cycle 24, actually, during sector structure, during near solar minimum. And I watched how the sector structure changed, and it was just unbelievable near the equinoxes how long we would have 5 nanotesla south magnetic field. We would have it for like 7 days in a row. And it was like, and it was just rock solid. And I was just like, oh my goodness. And that is not the other effect. The equinoctial effect, I can't pronounce that word. I never have been able to. Which was a bit more variable. But this effect was just intense. It was just really intense. So I've always been partial to it and paid attention to it because of the sector structure. It really does play a role. But yeah, it's not really at play right now because we're too close to the solstices. So hopefully that answers that question. Paul, who is my media contact? I am a media contact. I am a solo person here. So yeah, you can ping me. If you're on Twitter, you can ping me there. You can ping me at spaceweatherwoman@gmail. That's I think I'm on YouTube page. I will check that email. I haven't been able to check it recently, so if you want to ping me there, that's fine. You can easily ping me on Patreon too. I'm much more talkative there. But social media, you can get me as well. Facebook, I'm also on, so feel free to ping me that way. Okay, let's see. Is Solar Ham good to keep yourself updated? Oh, sure. Sure. Kevin's great. He knows a lot of good stuff. And he's wonderful for amateur radio. I used to support Kevin for a bit. I do on and off when I can. So yeah, you're in good hands there. Let's see. Oh, there were 2 massive ones directed at Comet 3 Atlas. Yeah. So it happens so often you think during a solar maximum, not just Earth facing. Right. This set of regions were extremely busy. And I'm sure there were some really great tail disruption events with Comet I3 Atlas that everybody freaked out about. Guys, we've been watching tail disruptions with comets for decades upon decades. They're very common. Just ask sun grazer comets, right? He talks about it all the time. I3 Atlas is not doing anything for the sun. I mean, the sun couldn't care. Mercury is much closer, much more massive, and yet you don't see space weather ripping across everything every time Mercury passes in front of Earth around the sun. It's not like we're getting hammered by space weather events simply because Mercury does a transit across the sun, right? Why would I3 Atlas, which is hardly coming inside the orbit of Mars, right? The moon Phobos, Mars's moon Phobos is twice the size of I3 Atlas. And you think it has any effect on the sun? Nobody talks about that, but oh boy, I3 Atlas comes by and everybody's up in arms about I3 Atlas. It's just crazy. Grifters, grifters, grifters. We have interstellar visitors all the time. Sun doesn't care. It really doesn't. We had Shoemaker Levy slam into Jupiter. What did Jupiter do? It yawned, right? Had like 8, the comet broke up, and it just slam, 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 and it was just like all these puddles across Jupiter, right in this like southern hemisphere of Jupiter. We all watched it almost live because we had Galileo at the time. I remember at UCLA we got to watch all of this stuff happen because we were part of the UCLA was the magnetometer team on Galileo. So we watched all this stuff happen live, and Jupiter just swallowed them up, just like throwing a stone in a pond. And we're like, Jupiter, do something. And yeah. Just ripples on the pond, and then they quietly dissipated. A few rotations. Jupiter rotates every 10 hours, so we got to see it back, pretty quickly. And we saw the scar like these mosquito bites, all the way across Jupiter, where all the shrapnel from this disintegrating comet went in and bang, 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 just piecewise, bang, 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 bang. And that was it. And it was like, okay. So if it's not going to do anything to Jupiter, what do you think I3 Atlas is going to do to the sun, just flying by it? The sun doesn't care. And all of these people that want to talk about this being a big, big deal and, you know, heaven and earth coming together, I'm sorry to disappoint you. The truth is sometimes disappointing. I'm sure it's much more fun to think of the fanciful stuff, but for those who get scared by it, please don't. It's fine, right? This stuff happens all the time, and it's not the end of the universe. It's not even the end of Earth. It's definitely not the end of the sun. Okay, so hope that helps to calm nerves. So yeah, Atlas is a distraction. Exactly, right? How often will X5 flares occur on any axis? You know, we only get a few a solar cycle that end up being that big. Now X1, X2, meh, we could get those quite a bit. And what do they mean? Sometimes they don't mean anything. Sometimes you just get a big radio burst for about 15 minutes and it's gone, and that's nothing, and you don't even get a coronal mass ejection from it, because that particular region has been so busy that it blasted all of the overlying material off it that it doesn't care. So you can get really, really big X flares, really, really big shock waves, big type 2 bursts, radio bursts along with that, as well as high frequency, you know, microwave radio bursts. It disrupts GPS, it disrupts communications, it frustrates people who want to launch on the Dayside, launch rockets on the Dayside. But outside of that, nothing. Nothing. Okay? So again, it's a bigger problem for our technology. And then again, you know, you can get a low X class flare or even an M class flare and get this massive coronal mass ejection. Or you can even not have an M class flare at all and just get a huge filament eruption, not even near an active region. So no big flare, maybe a C class flare just from the brightening of this thing ripping off the sun. And yet you can get a G4 storm from it, because the sun sends a whole zoo of stuff at us. So those of you who just pay attention to flares, don't. Pay attention to everything. You need to pay attention to solar flares and coronal mass ejections and the filaments, the big long worms on the sun. Those things rip off on their own and hardly leave a signature in the X-ray flux. Okay? The sun throws all sorts of stuff at us, and it does it differently. But does any of it ever mean the end of the world? No, it doesn't. Not even an X45. Right? We had the Halloween flares. We had a huge, massive X28 or something, super high, what should be classified as a Z-class flare, but we don't ever use that name because they're so rare. And what did it do? Did it end society? No. It caught a few satellite operators with their pants down, but we survived, right? And can it cause problems? Sure. But is it going to cause the catastrophic problems of 1859? No, it won't. We're smarter than that now. Okay, so we'll ride through it. Okay. Has Jupiter's red spot weakened since Shu Levy 9? Really? Do people actually try to correlate that? That'd be interesting to see if there's still some kind of thing so many years later. What was that, 1994? Something like that? When was that? When did that happen? It was a long time ago. All right. So, okay. Stephen Burns said the only thing was that the electromagnetic situation that Mercury, what, you think that because Mercury has a magnetic field that makes a difference, or doesn't have a magnetic field that it makes a difference to the sun? Again, I mean, there's so many orders of magnitude difference, and Mercury's magnetic field doesn't even stretch out to the sun. So the idea that it's creating that, I would be much more concerned about Jupiter and Saturn being electromagnetically connected to our star than Mercury, to be totally honest. And their gravitational pulls and their tidal pulls. If there were anything, I would be looking for linkages from that perspective. I mean, the whole reason why we have the asteroid belt where it is because of Jupiter and Saturn. So there are large-scale effects that those big planets, those big gas giants create for us. Jupiter were 3 times larger than it is, it would have ignited, it would have been its own star, and we would have been a binary star system. So Jupiter has an outsized influence on our solar system. Mercury does not. Okay. Anyway. All right, you guys are welcome. Any other questions, guys, before we close this down? 1859, catastrophic problems are minuscule to today's tech. That's exactly, and that is why space weather forecasters are so important. It's also why I'm training people with the SWEN program, is so that people will, so that we will have people who are ready and are capable of translating this information to engineers and be liaisons for engineers and scientists who are building the next generation of tech. And so that we also get credible space weather information for people like you, who then can talk to these other people and make them aware. Because the more people we have aware in a credible fashion, in a believable fashion, the better off we are. Because you guys end up being the mouthpieces of space weather. And it is important, because our tech, even though it's not critical for humans to survive, right? We've been surviving just fine with or without space weather. We're building in more and more susceptibilities to our power grids, to our aviation infrastructure, right? To our web infrastructure, our communication infrastructure. We're building more space weather susceptibilities all the time. And we are not necessarily taking space weather into account when it comes to that. And so we need that awareness, and we need folks like you out there fighting the good fight, talking the good talk, right? Not fear-mongering, but out there talking sense to folks so that they become space weather aware and space weather savvy. And who knows, maybe you will be the spark that lights up an engineer's mind and gets them to redesign something so that it's more space weather robust. Right? Or gets them to ask that question, hey, have we thought about what the space environment might be for this particular application? And they go, you know what? No, we haven't. Maybe we should. Let's go take a look, right? And the whole paradigm changes. I mean, sometimes that's all it takes. So that's really what my thrust is, being out here, right? Educating you guys with the right stuff, not the junk food, right? But the good food. The food that's going to make you healthy and strong and very space weather aware and savvy and able to carry on so that I don't have to become space weather grandma, right? I want to be up here with an aluminum walker, as I've teased about in the past, right? You guys have got to carry the torch when I'm ready to, when I'm too old to do it myself. So, counting on you guys. Okay. All right. One last look at the data. Yes, absolutely. Let's see if anything better's come. Oh. Boring. Let's put this in perspective. Let's do 3 days worth of data. Now, at least it's bigger than anything we've seen in the last 3 days, right? But see this big long set of legs? I think this is still kind of holding us back. I think that's part of what we're seeing here. I really don't think that this is the flank of the shock. I don't think that this is what we'd expect to see. I think there's more coming. And it's just trying to get around this massive structure that's holding us back. Let me zoom back in again. But yeah, right now, we're kind of in a holding pattern. Don't know if Adrian is out fighting, or looking for Aurora, if he's still here. But I don't know if Adrian's seeing anything yet. Still very little, very strongly radial. So that tells me, that's that yellow line again. That tells me that we're still in, either a sheath, hairy edge sheath region, or notice it's very continuous here. Notice this? It's very continuous. So what makes me think is that this may still be the legs of the structure. We just had a shock or a compression of this that propagated maybe up to here, and then maybe the shock died. Don't know. It's kind of hard to know the physics exactly what's going on in here. But this may be the structure behind it, slamming into the back of this one, and then part of it's propagating in. So you're still seeing field and stuff that's consistent with what we see before. Notice? There's a little bit of a change, right? Because we are seeing a little bit more. It's a little bit stronger field. It's not exactly the same. So there's a little bit more of a Y component now than we had before. But the Z component is still pretty much hovering around 0. The radial component is still pretty strong, right, at almost 10 nanotesla. The only difference is that we have had a deviation with the Y component. So maybe we have moved into a different regime. That's hard to say. It's just too early. But notice it's getting stronger. So that's another hint, as you see it getting stronger, that it's being compressed. So it's being compressed from the back end. The fact that this is dying down, yeah, I think this was a shock that propagated in. And this is still trying to die down, just like this speed profile was. If I go back then, again, not 6 hours, let me do 3 days. Zoom back out. Sometimes what helps to interpret data better is getting a larger picture. Instead of just zooming in on what's happening right now, zoom out, get a larger picture. See how this is a declining profile, right? Same thing here. It got maybe shocked up and then is declining. So again, this may still be the back end of this structure here. And as it gets compressed by this, it's really beginning to ramp up. But the speed is still trying to go down, just like it was trying to go down before. Really hard to tell. Really hard to tell. It could be a totally different structure, but it could also be a compressed end of this one. I think the only way we'll know for sure is just let more data flow in and see how things change as things move on. Okay. But, you know, a little bit here and there. Now we've kind of jumped down, maybe a little bit more magnetic field, you know, southward magnetic field. But at this speed, about 400 to 500 kilometers a second, you've got about 50 minutes to wait before this last bit of stuff actually hits Earth. So it's a little bit of a wait. 45 to 50 minutes, I think. Someone could do the actual calculations. I do one of those. So anyway, guys, any other questions? Because I've been on here for quite some time. I hope you enjoyed this stream. Sorry about the hiccup at the beginning, but you know, YouTube is what YouTube is. What is this? What caused much of Europe, Russia, and North America to be buried in water and mud around 1850? I don't know. I don't even know the incident that you are talking about. I'm not an historian, especially with terrestrial weather. So there's a lot of things that could be doing that. And trying to look at solar cycle variations with climate, the people I steer you toward are people like Scott McIntosh and Bob Lehman. We have historically looked at solar cycles the wrong way. We look at them from solar minimum to solar minimum, or from solar max to solar max. You know, we're always looking at solar minimum and solar maximum, and we really need to be looking at the peak of the change. How fast is something changing? So the ascending phase, the descending phase, where the sun is changing the most rapidly, where that is peaking, the change is peaking. That's where we need to be looking at in terms of climactic markers. And we're lining up, there are a lot more things that get lined up that way when you look at it from that perspective. Scott and Bob talk about terminator and pre-terminator, which are very similar to what I'm discussing by talking about the peaks of change. When the sun is changing the fastest is when Earth responds the strongest. And so they see cyclic changes in, let's say, La Nina and El Nino, for example. There are weather pattern changes, large-scale weather pattern changes that occur during these periods. But they've often eluded those who would look for them, simply because we organized the starting and stopping points of solar cycles the wrong way, really. We looked at the wrong things because we've been so used to looking at sunspots. And that's a great proxy for certain things, not a great proxy for other things, like the strongest influence our star has on Earth's climate. So I'd go look at Bob Lehman and Scott McIntosh's papers. They might actually have some insight into that particular event. Okay, guys. Anything else? I'm smarter now. Thank you. You're very welcome. I appreciate that, Kathy. That was kind of you. When will we see you on next? Actually, pretty soon, right? I might. I I try to do a forecast about once a week. I do more frequently on Patreon. Sometimes those shorty forecasts make it to YouTube. Sometimes they stay just on Patreon. It all depends. I've been working on a documentary, so it's kind of tough to get everything done. But you'll see. I'm going to be doing a mini course here soon. I had my Patreon family talked me into doing a mini course again, so I will start doing them. But yeah, so soon. Let's see. Yeah, let's get, oh my goodness, a high-tech replacement for Stereo B. I know, horrible. Well, we'll have one, which is Vigil. Vigil will be launched in 2030, I think now, sadly. And it will park at L5, and that will help. Because L5 is the point, like, if you're Earth and I'm the Sun, L5 is over here. So as I rotate stuff into your view, L5 sees it first. So that will be good. But that's not until 2030. It's a long time coming, but Stereo taught us that we really need it. So, yeah. Okay, let's see. Oh, you're welcome, Leon. Thank you so much. You're very welcome. And you're up late in Germany, so I appreciate you doing that. Yeah, check the CME, the CCMC CME scoreboard. That's a good place too. There's lots of, probably lots of good battles going on. They should make a betting pool about the CCMC scoreboard. It's where everybody puts their own models up and tries to get the impact time, or the impact time at Earth correct. It's cool. It's very cool. You're very welcome, Jerry. Okay, guys, have a great one. I hope this picks up. It looks like it will. It looks like, oh, this might be getting better. Okay, so don't lose faith, right? We still may be fighting the previous legs of this storm. We'll get into the big ones. They'll come, usually fashionably late, as always, right? So enjoy, and I'll talk to you guys soon, okay?